Good morning, everybody. This is Indira, Assistant Professor of Institute of Aeronautical Engineering from Department of Mathematics. In the last class, we have found how to calculate the eigenvectors and eigenvalues of the given matrix. Today, we'll extend the topic and we would like to find out how to diagonalize the given matrix. Now, first of all, going to the procedure, let us understand what do you mean by the diagonalization of the matrix. The diagonalization of a matrix, if a square matrix capital A of order n has n linearly independent eigenvectors x1, x2, so on up till xn corresponding to n eigenvalues lambda 1, lambda 2, so on up till lambda n respectively, then a matrix P can be formed such that P inverse AP is a diagonal matrix. I'll repeat once again, a matrix P can be found such that P inverse AP is a diagonal matrix. So here the P is nothing but we find it's a set of eigenvectors. P is nothing but the set of eigenvectors. Okay, so given that x1, x2, so on up till xn are eigenvectors of capital A corresponding to eigenvalues lambda 1, lambda 2, so on up to lambda n respectively, these eigenvectors are linearly independent. We'll define capital P as set of these linearly independent vectors. Since n columns of P are linearly independent, determinant of P is not equal to 0. Hence, there is a scope for the inverse of the matrix exists, that is P inverse exists. Now consider AP, which is equal to A into, as we have taken P as a set of eigenvectors. So x1, x2, x3, so on up till xn. Multiply each and every vector with A. Then A into x1, A into x2, so on up till A into xn. And this, the determinant of this matrix is nothing but, if you take all x's and separate these matrices, it can be written as P into D, where D is a diagonal matrix. That means it possesses only the diagonal elements. That means D can be written as lambda 1, 0, 0, 0, so on, 0, lambda 2, 0, 0, 0, 0, lambda 3, 0, and 0, 0, 0, lambda 4, so on. It can be extended. I have taken 4 into 4 matrix here, right? It can be extended to any order. So, AP is equal to PD, multiply both sides with P inverse. Then P inverse AP is equal to P inverse into P into D. Here, it can be written as P inverse AP is equal to P inverse into P into D. We all know that the matrix, the multiple of a matrix and the inverse is equal to identity. So, P inverse P is equal to an identity element. So, P inverse AP is equal to I into D. So, here we will get it as a diagonal matrix. So, we have that P inverse AP is always a diagonal matrix, right? Now, what do you call it? In this, we have two types of matrices, are the modal matrix and spectral matrix. So, let us understand what do you mean by the modal matrix and spectral matrix. The matrix P in above result, which diagonalizable, the square matrix is called modal matrix. That means P is called as a modal matrix. P is called as a modal matrix. And the diagonal matrix that we have obtained at the last is nothing but the spectral matrix. So, D is called as a spectral matrix. D is called as a spectral matrix. And P is called as a modal matrix. P is called as modal matrix. Modal matrix. Okay. So, here x1, x2, if x1, x2, so on up till xn are not linearly independent, this result is not true. Suppose capital A is a real symmetric matrix with n pair of pairwise distinct values, then corresponding eigenvectors x1, x2, so on up till xn are pairwise orthogonal. Hence, if P is equal to E1, E2, E3, so on up till En, where E is nothing but it's the matrix divided by the norm of each matrix. That is x1 divided by norm of x1, x2 divided by norm of x2, and so on up till xn divided by norm of xn. And P here is called as orthogonal matrix, and P will be orthogonal matrix. So if the modal matrix is orthogonal matrix, then P inverse is equal to P, because for orthogonal matrix A into A, matrix A is said to be orthogonal if A into A transpose is equal to A transpose into A is equal to I. So here there is no need for you to go for the finding out the P inverse. Just we can find out the transpose of the modal matrix and multiply it by A into P to get the required diagonal matrix. So this is how the modal matrix and the spectral matrices have to be calculated while diagonalizing the given matrix. So let us go and first let me recapitulate the procedure of finding out the diagonalization of the matrix once again. Suppose we have P, A is a matrix. A is a matrix which has to be diagonalized. Suppose A is a matrix which has to be diagonalized, right? Okay, so then the very first step is that we need to find out the eigen values. In the very first step, we need to find out the eigen values. So name it as lambda, right? Now, for the next step, we need to find out the eigenvectors for each eigenvalue. So you have to find out the eigenvectors for each eigenvalue, right? Okay, for each eigenvalue. After finding out the eigen vector, then you take the set of eigenvectors as a matrix P. A combination of eigenvectors as a matrix P. So I have taken P is equal to x1, x2, x3. Suppose if I have taken A as a 3 into 3 matrix, then my modal matrix is given by x1, x2, x3. Next step, the next step of the problem is we need to find out the P inverse of the matrix. We need to find out the inverse of the matrix. Okay, after finding out the inverse of the matrix, in the fifth step, we need to multiply P inverse with A into P. And obviously, when A is pre-multiplied by P inverse and post-multiplied by P, the resultant is nothing but the matrix D. We'll get a diagonal matrix containing the diagonal values in its diagonal. Okay, so D is nothing but a diagonal matrix with eigen values in its diagonal. So it contains the eigen values in its diagonal, and which we call it as the required diagonalization of the matrix, and this capital D matrix is called as a modal matrix. It is called as a spectral matrix. Modal matrix is a set of eigenvectors. So spectral matrix, D is called as a spectral matrix. So it's a very lengthy procedure. First we need to find out the eigenvalues. Next we need to find out the eigenvectors. Next take the set of eigenvectors, find out the P inverse and multiply P inverse AP. Then we'll get the diagonal matrix containing the eigenvalues in its principal diagonal. So which is called as a spectral matrix and required diagonalization of the matrix. So now this diagonalization of the matrix helps to find out the powers of the matrices also. So that is the advantage of finding out the diagonalization of the matrix. So let us calculate the powers of the let us see how to calculate the powers of the matrix. So we can obtain the powers of the matrix by using diagonalization. Now let A be the square matrix. Then a non-singular matrix capital B can be found such that D is equal to P inverse AP. D is equal to P inverse AP. Now, therefore, you multiply D into D. D into D is nothing but P inverse AP into P inverse AP into P inverse AP. Okay. Now, you club this P into P inverse. So, you separate this as P into A into P into P inverse, P into P inverse into A into P. Right? So, this you can write it as P into P inverse is nothing but identity matrix. So, this can be reduced to identity matrix in the next step, and A into A is multiplied to get A square P. Okay, so we got D square is equal to P inverse A square into P. Similarly, once again you multiply with D. That means once again you take P inverse AP in the right hand side. So we are going to follow the same procedure. We are going to get this matrix as P inverse A cube into P. So therefore D cube can be written as P inverse into A cube into P. So on and so forth. So D to the power of N is equal to P inverse A to the power of N into P. But we need to find out the powers of the matrix. So for this, you pre-multiply this matrix with the P on both sides. So if I multiply P on both sides, P into D to the power of N is equal to P inverse A to the power of N, P into P inverse A to the power of N into P. Again, the matrix, the multiplication of the matrix with its inverse is equal to identity. This I'll get to the right hand side as A to the power of N into P. Again, you post to multiply with the P inverse on both sides. So, P into D to the power of N into P inverse, and which is equal to A to the power of N into P inverse. Once again, you use the same identity, that P into P inverse is equal to A. Therefore, you can get that A to the power of N is equal to P into D to the power of N into P inverse. So, if you have the modal matrix in your hand, then it's easy to calculate the powers of matrix and very easily. Just multiplying the given diagonal matrix with the P and P inverse, the respective matrix will give you the value of A to the power of N. So this is how we can find the powers of the matrix by using the diagonalization of the matrix. Okay, so here to obtain A to the power of N, pre-multiply by P and post-multiply by P inverse. So, P into D to the power of N into P inverse is equal to P into P inverse into A to the power of N into P inverse. So, therefore, A to the power of N can be written as P into D to the power of N into P inverse. So, this is how we can find out the powers of the matrix using diagonalization. So, let us go with one example of how to diagonalize the matrix. Okay, determine the modal matrix capital P of -2, 2, -3, 2, 1, -6, -1, -2, 0. Verify that P inverse AP is a diagonal matrix. Now, first we would like to find out the eigenvalues for the given vector by calculating the characteristic polynomial equation, that is determinant of A minus lambda I is equal to 0, where lambda represents the eigenvalues. So directly you can take the determinant by replacing the diagonal elements by A minus 2 minus lambda, 2 minus 3, 2, 1 minus lambda, -6, -1, -2, 0. Okay. So they take the determinant of the matrix, and it's which gives lambda minus 5. Lambda minus 5 into lambda plus 3 whole square is equal to 0, or lambda is equal to 5 comma minus 3. So 5 comma minus 3, where lambda minus 3 we have twice here. So as it is a 3 into 3 matrix, so 5 comma minus 3 comma minus 3 are the eigen values. So let us find out the eigenvector for each eigenvalue that we have find it, right? Okay, so let us first consider lambda is equal to, the first case, lambda is equal to 5. Okay, as we have seen in the last session how to find out the eigenvectors, the same procedure will follow. That means A minus lambda I into x is equal to 0, where x is the eigenvector that we need to find out, right? Here lambda is equal to 5. So A is the matrix that he has given. Let us suppose that X is equal to X, Y, Z, right? X, Y, Z. So which is equal to 0, 0, 0. So by solving this, by using the procedure, by reducing the given matrix to echelon form or upper triangular matrix, so do the forward substitution or backward substitution to get the values of x1, which is equal to 1, 2, minus 1. Similarly, we'll try to find out the eigen values for lambda is equal to minus 3, which is a eigenvector for the another eigenvalue lambda is equal to minus 3. So we can have two linearly independent vectors, that is x2 which is equal to 2, minus 1, 0, 3, 0, 1. So now I have in my hand all the three vectors which are required to frame the modal matrix. So x1 is equal to 1, 2, minus 1, and x2 is equal to 2, minus 1, 0, and x3 is equal to 3, 0, 1. Take the set of these three vectors, which is nothing but the given modal matrix. So the modal matrix is just nothing but the row wise 1, 2, 3, 0, 2, minus 1, 0, minus 1, 0, 1. So which is called as a modal matrix. Now let us find out whether calculate the determinant of this of the modal matrix. Determinant of the modal matrix, it comes out to be minus 8, which is not equal to 0. Therefore it is non-singular matrix. Therefore the inverse exists. So we'll follow the finding the next step. The next step of the diagonalization is finding out the inverse for the modal matrix. So P inverse is equal to adjoint of P by determinant of P, which is equal to minus 1 by 8, which into minus 1, minus 2, 3, minus 2, 4, 6, minus 1, minus 2, minus 5. Right? Okay, into the determinant, that is nothing but minus 1 by 8. So we are going to get it as P inverse AP, which is equal to, upon calculation, minus 1 by 8, and the diagonal elements are minus 40, 0, 0, 0, 24, 0, 0, 0, 24. Divide each and every element with 8. Each and every element with 8, we are going to get it as 5, 0, 0, 0, minus 3, 0, 0, 0, minus 3. You can remember that 5, minus 3, minus 3 are nothing but the eigen values for the given vectors. So the diagonal elements after diagonalization are nothing but the eigen values for the given vectors. So you can check yourself whether you're going correct or not by last if you get the eigen values. So the diagonalization of the matrix is diagonal of 5, minus 3, minus 3. Hence P inverse AP is called as a diagonal matrix, and this diagonal matrix is called as a spectral matrix. We call it as a spectral matrix. So this is how we can able to find out the diagonalization of the matrix. And let us go with another example of finding out matrix P, which transforms a matrix. Now I have another example. Find a matrix P which transforms the matrix A, which is equal to 1, 0, minus 1, 1, 2, 1, 2, 2, 3 to diagonal form. Hence calculate A to the power of 4. Hence calculate A to the power of 4, right? So extension for the problem is we need to find out the fourth power of the given matrix by using the diagonalization method, right? So let us first find out the eigen values for the given matrix. So the eigen values can be obtained by determinant of A minus lambda is equal to 0. A minus lambda is equal to 0. So that is nothing but 1 minus lambda, 0, minus 1, 1, 2 minus lambda, 1, 2, 2, 3 minus lambda is equal to 0. Solve the given determinant. We are going to get it as lambda is equal to 1, 2, 3. So these are the three distinct eigenvalues that we have got for the given matrix. Okay, now next we'll try to find out the eigenvectors for each eigen value that you have, right? So let x1, x2, x3 be corresponding eigenvectors for the given matrix. Then lambda is we can have you can able to find out the x by taking matrix A minus lambda into x is equal to 0. Substitute everything here, right? Introduce the given, and now you substitute the lambda is equal to the eigenvalues which we have got, that is 1, 2, 3. So upon substituting the eigenvalues, lambda is equal to 1, 2, 3, we are going to get the value eigenvectors x1, x2, x3. So here x1 is 1, x2 is minus 1, x3 is 0. So the eigenvector for lambda is equal to 1 is nothing but 1 minus 1, 0. Follow the same procedure for finding out the eigenvectors for the next two distinct eigenvalues, that is lambda is equal to 2 and lambda is equal to 3. So lambda is equal to 2, we have minus 2, 1, 2 whole transpose, and for lambda 3 we will get it as minus 1, 1, 2 whole transpose. Now I have the required eigenvalues to frame the modal matrix which helps to diagonalize the given matrix. So the P matrix is nothing but the set of 3 eigenvectors, which is nothing but 1 minus 1, 0, minus 2, 1, 2, minus 1, 1, 2. Now in the next step for the diagonalization, we need to find out the P inverse, that is inverse of the matrix. That is P inverse is equal to half into 0, 2, minus 1, 2, 2, 0, minus 2, minus 2, minus 1. And now we have P inverse AP. Calculate the value of P inverse AP, which already it's a value, and the P inverse is already calculated here, and A is the matrix that he has given, and P is a modal matrix that we have got. So after multiplying these three, we are going to get the spectral matrix, the diagonal matrix with the eigenvalues in its principal diagonal, that is 1, 0, 0, 0, 2, 0, 0, 0, 3. So here this is how we can find out the diagonalization of the matrix. Now extension for this question is we need to find out a to the power of 4. Already we have seen how to find out a to the power of n. A to the power of n is equal to p into d to the power of n into p inverse. So already p inverse is calculated, and p is a modal matrix that we have already got, which is nothing but the set of eigenvectors. Now we need to find out here the a to the power of 4. Now you substitute n is equal to 4. So a to the power of 4 is equal to p into d to the power of 4 into p inverse into p inverse. So substitute all the matrices p inverse and d to the power of 4. So which we are going to get it as minus 49, minus 50, minus 40, 65, 66, 40, 130, 130 and 81. This is nothing but the a to the power of 4 matrix. So this is how we can find out the powers of the matrix by diagonalization. Okay, once again I'll repeat once again how to find out the diagonalization of the matrix. Now for a given square matrix capital A, in the first step we need to find out the eigenvalues. Now the next step we need to find out the eigenvectors for each eigenvalue. Okay, next in the third stage we need to find out the modal matrix, which is nothing but the set of eigenvectors. Now in the fourth stage of the problem, we need to find out the P inverse. Now by using any method, either by Gauss inversion method, or you can have the joint of A by determinant of A model. By calculating the minors of each element, you can able to find it out, P inverse. And after finding P inverse, then in the fifth stage we need to find out P inverse into A into P, that is triple matrix multiplication, which we are going to get the diagonal matrix, and which contains the eigenvalues in its principal diagonal. And we call P as a modal matrix and D as a spectral matrix. So here for these questions we may get the extension of the question to find out the powers of the matrices. Suppose if you are needed to find out the a to the power of 5, then just p into d to the power of 5 into p inverse, which already we have calculated p inverse and p. So d to the power of 5 is just diagonal the matrix, which can be calculated very easily. So multiply these three matrices to get a to the power of 5 directly, the power of the fifth power of the given matrix. So this is how this diagonalization of a matrix is helpful. As this procedure is very lengthy, we need to find out some methods whether all matrices are diagonalizable or not. Okay, all matrices cannot be diagonalizable. Okay, few matrices are diagonalizable based on some rules and conditions. That we'll see it in the next session. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.